we can continue. Okay, so now now basically models allows us to perform limited number of experiments or prevent any further experiments, and sometimes prevent any experiments. Okay, now you know, there are cases where experiments can be easy. Experiments can be easy, or they can be very hard or impossible. Okay? I mean, if you're, for example, working with, I don't know, a small mechanical system, you can mechanical system or a simple circuit, you can easily experiment with it. If you have, let's say, a nuclear reactor, it can be very hard and dangerous to experiment with it. I mean, think about, for example, the Chernobyl disaster, right? They had been experimenting with a certain feature of the reactor when things basically got out of hand. Think about space exploration, right? Space exploration, orbital mechanics, okay? It can be impossible or very expensive to experiment. So we use models basically to models can be used to limit or eliminate need for experiments obviously provided that enough experiments, or enough understanding of the system exists to build a very accurate model, and that needs no verification. Okay, or there has been generations of experiments that actually led to the models. I mean, think about, for example, orbital mechanics. Okay, people started observing celestial bodies to build those models, and mathematical models made it possible to actually send spacecraft to the orbit. Okay, so at the time where people have sent rockets to the orbit, there was enough confidence in the models that they simulated everything in order to eventually generate a successful launch of a rocket, basically. Okay. If you remember SpaceX's video that I had shown you guys, or some of you guys, at the start of EE407, there has been small number of experiments that supplemented the mathematical model in order to build a successful self-landing rocket in their case. Okay. Now we come to the question of how to build mathematical models. Okay. Now, let me try to break it down. I mean, you can have obviously collective experience of experts, in the field. This corresponds to itself a lot of prior experiments. So you kind of exploit the accumulated knowledge in the area. This can also be collected from literature in the area. So you basically research what is already known in terms of the physics of the phenomenon. Okay, and this includes laws of nature, uh, such as Newton's laws and so on, uh, which were worked by generations of scientists, right? Generations of scientists and engineers. Okay. Now let's call this item 1. Okay, so this is one way of uh, building mathematical models. We can also have the actual physical system and experiments on it or with it. Okay, let's call this item 2. And we use mathematics, right, as item 3. Mathematical tools and methods to build a model of the system. Now what is interesting about these 3 items is that they can actually be conducted by different people. For example, 1 and 2 is very domain specific. Okay, so we really need to have a very good understanding of the field that the model is in. I mean, for this you need, let's say, doctors, physicists, engineers, different types of engineers. I mean, if this is a chemical model, you need chemists, you need chemical engineers in the loop. Okay, depending on other models, you may need biologists, economists, social scientists, etc. Okay, so this cannot be done by just the control engineer himself or herself, but needs collaboration with people from the domain. Okay, but if you take a look at, there is obviously an overlap. Okay, if you have the system, a control engineer may also be able to experiment. So 2 and 3 is basically the task of the control engineer. Sometimes in other disciplines, it can also be called a knowledge engineer. Knowledge engineer, because basically you transform the system knowledge into models of the system. Okay. So what do we do? The first step is to build a model. So we can call this physical modeling. This is usually followed by another step that we will spend some time on. It's called system identification. Okay. Now, what is the difference? Now, the difference is, in the first case, in the physical modeling, you basically break the system into its simple subsystems. Use subsystem models and I'm going to show you an example of that in a minute. Models to constructively arrive at a complex model. Often we use block diagrams for that, and you have seen some examples in 302. Block diagrams is not only a representation, but it's also a tool that you can use to constructively, step by step, sub-block by sub-block, you can construct a physical system model or a mathematical system model. Okay, so what is the difference of system identification? System identification is that you use the model, the often incomplete physical. Nerede? Subsystem models to constructively arrive at a complex model. Sorry, this pen is very slippery, so it's kind of an unstable system that I'm trying to stabilize on the screen. So I'm going to try to kind of break the letter down just a bit. So use the, is there any other questions related with any other words that... So system identification is using the incomplete model plus experiments to determine model parameters. So you can call this kind of filling in the model. Okay. For example, if you have a physical object, and in the model you have the center of gravity of the object. So it's very difficult to directly measure the center of gravity of this object. So you perform certain experiments which directly depends on the center of gravity, and the results of those experiments tell you where exactly within that physical object the center of gravity is. So this is system identification. Okay. Now we will come back to this system identification, and in fact I'm going to show you an example. But now I want to really show you an example, and this example may actually kind of be divided in towards the tomorrow's lecture as well, because I want to first conduct this small exercise that we have. So let's break at this point for about 5 minutes, a couple of minutes. Please go to your MetuClass website, and I'm going to try to let me hold on. So I will just open up our session exercise. I will make it visible, and I'm going to give you a couple of minutes to work that out for me, okay? So let's, sorry, it logged me out of the system, so let's make this visible. And I'm gonna start the exercise for you. Are you guys ready to go? Okay, so I'm just starting the quiz now. Is there anyone who is not able to see the exercise? All right. Now, guys, let me tell you something about these small exercises. I've made it possible to kind of have multiple attempts. So if you feel like you missed that point and you are not sure, I think the quiz allows you to try a response, and instead of just submitting your result, you just click, I don't remember the exact name of the button, but show me or check or whatever. And it's going to show you whether your current attempt is correct or not. And there is a small penalty, so not a very small penalty, but about 30% penalty. So you can actually make another attempt, okay? So that this allows us to basically have at least a non-zero score, even if you kind of missed that point. It's still that counts to your attendance, basically, okay? Okay, thank you. I guess that just concluded. So let's go back to my screen. Sadece bir soru vardı, evet. Herkes tamam herhalde. Tamam. Okay, so let's go back to my shared screen. So I'm gonna let me see. Zoom, share screen. Okay, and let's have sorry, let me save this note first. Where is the note? So let's save this note and let's have another note. Okay. All right. Okay, so now let me go over an example. Unfortunately, I couldn't kind of fine-tune the timing, so this example is gonna have to be broken down towards tomorrow's lecture as well. Okay, so this example is basically an industrial heating process. Of a mixture in a tank. Okay. The good thing about this example is that it has many components, and it's going to show us how we can step by step analyze a complex system in order to come up with a mathematical model. In this case, the mathematical model will be in the Laplace domain. It's going to be as a block diagram. Okay, so this block diagram, obviously you can manipulate it to obtain, for example, a transfer function. But the block diagram in this case will be actually a tool for us. We will use the block diagram to gradually work out the system model. Okay, so I'm going to try to sketch this system for you. It's going to be quite a complicated sketch. Okay, so here we go. So there is a tank, and let's start with the output. There is a thermocouple. Thermocouple is a device that measures temperature. Okay, so we have a thermocouple here. There is some propeller that is mixing this tank. Okay, so there is a heating pipe going in. Okay, let me try to kind of. So the way that the tank is heated is that heated steam is pumped into the tank. Okay, so this is a heating pipe. The waste steam is exhausted. Okay, so this is steam exhaust. Okay, And the system's output basically is the temperature of the mixture. Let's call this temperature theta. Okay, and this is basically our output. Okay, so the system's output, in fact, the variable that we are trying to control is the temperature theta. Okay, the input to the system is yet undefined, but it's going to be defined as a voltage. Okay, so what we are doing is that we pass this steam through a valve. Valve is a mechanical device that controls the flow. Okay, so this steam flow is coming from a valve, from essentially a boiler that generates the steam. So the valve controls how much steam is actually passing through. Let's call this flow, steam flow Q. Okay, so there is a valve that controls the steam flow, and the steam heats the mixture in the tank, and that is being measured by our thermocouple. Okay, so let's try to work this out further. So the thermocouple generates basically a voltage that is representation of the temperature theta. So we pass this through an amplifier. The amplifier's job is to transform the temperature as a very small voltage into a meaningful voltage that we can use. Let's call this voltage plus minus B. Okay, so what we do is that first of all, let's work maybe what happens with the valve. Okay, so the valve is a mechanical device. We control this valve through an electromechanical device. Okay, this is a solenoid basically. A solenoid is essentially a linear motor. Okay, you apply a voltage and a physical object moves within the solenoid, and that relates with the current that you pass through the coils. So if I try to sketch this, this is a solenoid. Okay, and you basically have in this solenoid a coil. Okay, let me show the coil with a different color. Sorry. So we go in, right? Go like that. So this is our coil. Okay, and this is the current flow. Let's call this the IS current. And the coil, the solenoid, is a block where it has certain parameters. For example, it has internal resistance R, it has inductance L. That's the electrical part, and I'm going to draw it when we will be developing its model. But we also have the mechanical part of this solenoid, and that has a certain mass M, and friction coefficient B, and also a coefficient Ks, which is going to determine how the current is actually transformed into force in this solenoid. Okay. Any questions at this point about any parts of this system that I've already laid out? Valve sonuçta şöyle, solenoid valve denilen obje sonuçta bir çeşit lineer motor. Yani bir akım uyguluyorsunuz. Akım coil'den geçiyor. İçindeki küçük bir şaft sizin geçirdiğiniz akıma göre hareket ediyor. Bizim buradaki problemimiz de bu hareket yukarıdaki valve solenoid controlled olmuş oluyor. Solenoid controlled. Yani benim geçirdiğim akıma bağlı olarak valve'in hareketi ve o harekete bağlı olarak flow'un kontrol edildiği bir durum var. Bunun birazdan tüm matematiğini çıkaracağız. Şu anda sadece fiziksel olarak objeleri ve o objelerin bir çeşit parametrelerini buraya yazmaya çalışıyoruz. Anlaşıldı mı solenoidin fonksiyonu?
Evet hocam, teşekkür ederim.
Is there any other questions related with any other part of the system? Evet. Birazdan, yani daha doğrusu denklemlerini çıkartırken zaten detaylandıracağız. Ama sonuçta bu bir motor olduğu için içinde hareket eden şaftın bir ağırlığı, değil mi? Bir ağırlığı, çevresindeki etrafındaki sleeve ile bir sürtünmesi, dolayısıyla mass, friction ve bir de akımın kuvvete dönüşmesiyle ilgili bir çeşit motor konstantı olmuş oluyor. Ks dediğimiz. Birazdan denklemlerini yazarken daha açık anlaşılacak. Başka soru? Any other questions?
Hocam, bir şey sorabilir miyim?
Sure, that's what I mean by a question.
Heating pipe ne işe yarıyor? Hani buhar giriyor ya zaten. Onu anlayamadım.
Şöyle söyleyelim. Tank filled with liquid mixture. Bunu ısıtıyoruz. Isıtma yöntemimiz içindeki bir borudan sıcak buhar geçirmek. Buharın akışı Q ile verilmiş. Akışı valve ile kontrol ediyoruz. Valve'i ise solenoid ile kontrol ediyoruz. Boiler sabit bir basınç sağlıyor ve bizimle ilgili değil. Yani Q akışının magnitude'unu biz valve ile kontrol etmiş oluyoruz. Ne kadar çok yani denklemle onu ifade edeceğiz ama sonuçta sıvının içinden akan sıcak buhar sıvıyı ısıtmış oluyor. Aslında bizim okulumuz bu şekilde ısınıyor. Yani okulun içerisinde sıcak buhar dolaşıyor. Okulun altındaki kanallarda. Bu sıcak buhar bizim binalarımızın içerisindeki bir takım sıvı tanklarını ısıtıyor. O sıvılar da sizin kaloriferlerinize gelip oturduğunuz odaları ısıtıyor. Açık mı?
Hocam onu anladım da şu pipe olayını anlayamadım. Heating pipe dediğimiz yukarıda bir karıştırıcı mı oluyor?
Hayır. Heating pipe şurası.
Tamam hocam.
Şu mixer diyelim buna. Mixer'ın amacı sadece tankın içindeki sıvının homojen bir ısıya sahip olduğunu, yani termocouple'ın ölçtüğü yerle sol üst köşe farklı değil. Mixer sonuçta ısıyı homojen bir şekilde tankın içine dağıtmış oluyor. Anlaşıldı mı?
Tamam hocam.
Is there any other questions? Okay. So let's continue with what happens at the location we derive the solenoid. So what's happening is that I have essentially a potentiometer here. Sorry, let me make the potentiometer a bit larger. Okay. So this end is like basically a ground, you might call it. Okay. It's an electrical, sorry. Okay. So we might call this our ground. Okay. So what happens is that from here we take a voltage that goes into an amplifier. And that's going to have a gain of Ka, and that will generate an amplified voltage that I call plus minus V. Okay, and over here this amplifier's input is also connected to the other amplifier. Okay, so over here we have a voltage R. okay, and across this resistor, and over here we have a voltage that we call E. So what's happening is that over here, in fact, there is a comparison device, okay, and I'm going to write down the equation in a minute, but essentially what's happening is that the reference voltage R and this amplifier voltage B over here determines what's going to be the voltage E by simply the Kirchhoff's voltage law. Okay, so that error voltage, what we call an error voltage, is amplified to generate V, and that drives the solenoid. Okay, so this basically lays out our entire system at this point, and we can start kind of working out the equations. And I'm going to start with that, but we will not be able to finish it today, so we will continue tomorrow. Okay, so let's take a look at physical components one by one. We will start with the thermocouple. Okay, so in fact, thermocouple and amplifier. Okay, so let me mark that as one. Thermocouple, and amplifier. In fact, later on we will call this the sensor part of it. Okay, so this is the sensor part. You see that the output is measured by the thermocouple, and an amplifier converts it into a voltage that is meaningful to compare with something else at the input. Okay, so let me write down what's the equation that we have here, okay, which is going to be quite simple. So the voltage, the very small voltage generated by the thermocouple is amplified. So this gives us an equation that gives us B in terms of theta. So KB theta. So this is one of the equations that comprise this system. Okay. So we have the output temperature theta over here, right? Theta is measured and converted into a voltage B. So that essentially covers the thermocouple and the amplifier part of our system. Okay. Now the second part that I want to look at, and I'm going to call this 2, is basically what's happening here. Okay. So there are two things that are happening here. First, a voltage E has to be calculated. And also there is an amplifier that converts that voltage into its output voltage V. Okay, so let's call this 2. Comparator, and controller. Later on we will see that in fact this part is the comparison device, and the controller. In this case, this is simply a p-type controller, a proportional controller, a simple gain. Okay, so let's write down the equations of that part. Okay, so the actuating signal, this is our terminology. Actuating signal V is generated as follows. First, we need to calculate the input to it. Okay, so sorry, I'm going back and forth, and there is a latency, I believe, so that makes it a bit kind of shaky. So let's write the Kirchhoff's voltage law here. Okay, so we have plus B right? So plus B minus R plus E is equal to 0. So that gives us why we call this a comparator block, because E is equal to R minus B. So that's one of the equations. So you see that I'm comparing the reference signal with a converted version of the output, which is B, and the difference gives us the error signal. Okay, so this is Kirchhoff's voltage law. Kirchhoff's voltage law. Okay, and also the amplifier basically gives us the second equation, which is that V is equal to Ka times E. Okay, so that difference signal E, which we often call the error signal, is amplified. Okay, so the error signal is amplified to drive the solenoid. Okay, all right. So now we will continue, I guess, tomorrow with 3 and 4, okay, which is basically that 3 will be the electrical part of this solenoid, and I'm going to continue with 4, which is the mechanical part of this solenoid. So what's happening is that this voltage V will be driving the electrical part, the electrical part will be driving the mechanical part, and we will continue from that point on. Okay, so I want to basically break at this point and take your questions, and after that we will finish for today. Okay, now do you guys have any questions related with this part of the lecture?
Hocam actuator'ın bir tanımını bir daha yapabilir misiniz?
An actuator is basically something that drives the plant or process. In this case, the plant or process is basically starting with the flow of the steam. Okay, so the input to the plant is actually hot steam flow, and its output of the plant is the temperature of the fluid. Okay, so an actuator is basically something that drives the plant. In this case, this solenoid actuated valve is the actuator of this system. Okay?
Thank you.
Any other questions? Okay.